Hi all, welcome to the seventh part of the video lecture on complexity theory. See, in the last part we discussed in detail this reduction and that satisfiability problem is what we seen in detail, circuit satisfiability formula and CNF satisfiability. So now we are moving on to a different problem, say click problem, and this is something again I discussed already, and now we will see how this click problem can be shown as an NB complete problem. So how we can show that reduction from an already proved NB complete problem. So we'll be choosing that three-side problem that we discussed in the last video. So to understand why three-side is NB complete, I request you to watch that previous videos and come to this, especially that part 6 at least. Now here we assume that the satisfiability problem is particularly three-side problem is NB complete, and from that point we will prove what about this click. How from every problem we can have a polynomial reduction to click. Okay, so what is click basically? So given any graph, say g of v comma e and an integer k, does the graph contains a click of size at least k vertices? So basically I told you what is click. Click is the maximal complete subgraph of the given graph, right? So we are interested on maximal click, or the one with the maximum cardinality, we call it as maximum click, maximal difference, everything I discussed in the previous videos, please watch it. And now we are just looking at the decision version only, and any optimization problem, say finding minimum or finding maximum, you can solve by asking series of decision questions. Okay, so we are just looking at the difficulty level of the decision problem. If decision problem itself is NB complete or NB hard, definitely the optimization version will be more tougher, right? So that is straightforward. So look at the decision version and see its complexity. So already a graph is given, and you are just supposed to check whether it contains a click of size at least k vertices. So k vertices, k plus 1, like that. So at least k vertices is what you have to check. Okay, and we will see. This problem is a well-known NB complete problem, and we are going to see its proof. So first of all, it is NB, and it is straightforward, and there is no polynomial solution available, and given that this is a click of say k vertices and all, you can verify that in polynomial time. So you can call it as a non-deterministic polynomial algorithm. The existing brute force kind of algorithm is coming under this category, and there is no easy polynomial solution that is being discovered by anyone so far, and we don't know whether someone will come up with a polynomial solution in the future also, but at the same time we are going to relate it with some of the similar problems. So that is what we are going to do. Okay, so its hardness, NB hardness, reduction from all other problem to this particular problem, that we will do through three-side problem, because three-side is already known to be an NB hard problem. So if I can have a mapping from three-side to click, that is enough. I done the job, right? So that's all. So basically, this is a graph theoretic problem, right? Click, but satisfiability is something from discrete mathematics or digital electronics. It's a different from a different domain. Now how that these two things can be mapped basically? So ultimately I just need a graph, then only I can talk about this click and all, right? So given any Boolean algebraic expression, how you can convert that expression into a graph? So I already told you what is a clause and all, hope you remember. So here I have a Boolean algebraic expression having two clauses, say two clauses, and the first clause is containing x1, and if it is in conjunctive normal form or disjunctive also, you can think about it. So by default it is conjunctive normal form, and which is conjunction of clauses, and each clause is a disjunction of literals, and the literals are like x1 is there and x2 complement is there, and then or x3. So this is one of the clause, and that is represented like this. So these are all the literals of the clause, like that. And here I have another clause. If it is in CNF, it will be of the form x1 or x2 or x3 complements, like that. Now how you can map this into a graph? So what you have to do is, for every literal in every clauses, there is a vertex in the graph. Okay, so you can have vertex for x1, x2 bar, okay, x3. And similarly again for x1 you have to repeat, because whether the variable is repeating or not, you have to give separate vertex. So that is the first rule, x2 and x3 bar. How people come up with this kind of a graph and all, that is the secondary thing. I am directly giving you the solution, okay, how to draw the graph and how we can prove that this is this mapping is correct. Okay, so that you have to formally do. Now What about the edges? So edges are drawn between clauses. So that is very important. So within a clause, we have literals like x1, x2 bar, x3, etc. here, and there is no edge between them. So there is no edge say between vertices of same clause, but instead we have a edge between vertices of but I mean literals correspond to two different clauses. And one more rule is like there should not be an edge from a variable and its negation. Say x1 and x1 complement, x2 and x2 complement. Like that, there should not be any edge. So if you are looking at the first clause, the first literal is x1, okay, and from x1 I can have a edge to other clause literal, say x1 to x1, it is fine. If it is bar, it is not fine, okay, but as it is normal x1 only, I can have an edge like this. Now similarly from x1 I have an edge to x2, and x1 I have an edge to x3 complement. This is fine because they are two different variable and its own negation. I should not have an edge, okay. So here you can see. So I hope this part is clear. Similarly, when I am taking the next variable negation x2, I can have an edge with the x1. This is fine, but I am not supposed to have an edge like this. This is not allowed. Why? Because now this edge is going from x2 complement and x2, a variable and its own negation. This should not be there, but I can have an edge from negation x2 and x3. That is fine. So this is how you have to draw the graph. How the graph construction is clear. Simply draw edges between literals of two different clauses in such a way that there is no edge from a variable to its negation. That is important. So one vertex per literal per clause. So how many clauses are there? Say k clauses are there and 3 is that problem. Then there will be 3k vertices. 3k in the sense there are k clauses and it is 3 set problem. So that every clause is containing 3 variables. There are 3k variables. So 3k vertices will be there. Okay. That is the first thing. And what about the edge? Edge between the vertices in different clauses. Between different clauses, you have to draw the edge. That is important. Except from xi and negation xi. That should not be there. Okay. Between two different clauses. Other than this situation, you can have an edge. So if I have m clauses, so or say k clauses or m clauses, whatever it is, then look for a clique of size m. So basically, it is this how these two problems are related. In the given satisfiability, I mean Boolean expression, if I have a k clauses or m clauses, so this is one of the clause. So this is the first clause, say c1, and this is second clause, say c2. Similarly, if I have etc some cm number of clauses, and suppose the formula is satisfiable, then I can say definitely in the corresponding graph there is a clique of size m. Similarly, if in a graph I have a clique of size m, definitely the corresponding Boolean expression represented by the graph is going to contain a satisfiable assignment having same clauses. So both are, it's a bidirectional proof. Fine. Yeah, that about it. Now we have to see how these things are related. So here I given some proof, but before that I will take one more example and tell you in detail how these things are related to each other. Okay, let me draw this example here and I will continue then after. See, this is as one example formula is taken. Some you can see every clause is containing two literals, so it is basically asking two satisfiability. But anyway, I already told it is polynomially solvable. But to see this mapping, I'm just taking it as an example. You can either take any say in general some LSAT problem you can think about, right? I mean one clause is containing say L literals. That is what I mean. So the mapping is something common for everyone, and the rule says that suppose I have a Boolean function with the k clauses. Say this is my function f c1 c2. So here I have a clause 1, this is clause 2, and this is clause 3. I have just 3 clauses, but in general I can have a k clauses, right? If that is the case, what about a particular clause? One clause is containing say I am numbering like this. So the first literal in general I am calling it as say y clause number, then literal number y11, and let it be say y clause number 1 second literal, like that, and let it be y. Generally I am using that notation y, and clause number 2 first literal, and let it be clause number 2 second literal, and this is clause number 3 first literal. So like that you can give, and each literal I am talking about literal, it can be a variable or its negation. Okay, fine. So accordingly, so if we are looking at it, it can have some L literal. In our example, as it is 2 set, only 2 literal, so it can go up to some L value. Okay, so that is a clause. Now that kind of a formula I am mapping into a graph, and how I am making the vertices of the graph. Vertices of the graph are all, I mean ij, two indices ij, where I corresponds to the clauses. If there are k clauses for each clause, I have a some L number of literals are there, right? So accordingly I am giving name to these variables. Okay, so basically just like this, for example, this is my clause 1. For clause 1, the first vertex is something denoted by 1 1, that's all. Similarly for clause 1, the second vertex is denoted by 1 2. So this is clause number, is the first index, and the second index is that literal numbering. If there are L literal, 1 1, 1 2, etc., 1 L. Similarly 2 1. So in general for clause ij, like that it will go. Okay. So if you are looking at this graph, what is your how many literals are there? There are 6 literals totally. So there are 6 vertices, and I am naming them like this. So basically this 1 1 is nothing but clause 1 literal 1, it is y1. Similarly this is clause 1 literal 2, that is y2 complement. So this is a literal, right, a variable or its negation. Similarly clause 2 literal 1 is y2, and clause 2 literal second literal is y3 complement, right? You can see here. Similarly for clause 3, y3 and y1 bar, right? This is y3 and this is y1 bar. Okay, like that. Now what about the edges? So I have an edge between two different clauses, and within a clause there is no edge, that I already told you. So the edges are between two such vertices, say ij and kl, such that I not equal to k. I not equal to k means first index corresponds to the clause number. They should belong to two different clauses. Edges are only between two different clauses and not between I can't have an edge like this, because both literals are within the same clause, right? That should not happen, but it should be between different clauses. And also if we are looking at the actual literal, it should not be complement to each other, like the literal corresponds to this ij is actually, say literal, say x ith clause and jth literal xij, and here it is xkth clause and lth literal xkl, and xij and xkl, they should not be complement to each other. So that is this checking. Accordingly you can have edges. So let me tell you how to draw edges in this graph. So let me first take this y1. Within the class there is no edge, and you can think about edge from y1 to clause 2. Clause 2 I have y2, there is an edge, okay fine, and clause 2 I have y3 complement, that also fine. Why it is? Because they are not complement to each other, and between two clauses you can have edge. Similarly y1 and y3, two different clauses and not complement to each other, and y1 and this was actually this third clause second literal was y1 complement, and see there should not, if I am drawing an edge like this, this is wrong, this is not allowed. This is because this is y1 and this is y1 complement, this xij and xkl complement, that should not happen. Okay, so that is not allowed, so I am removing that. Fine, this is not allowed. This is what we are trying to say. Fine. So y1 is fully covered. Now if I am looking at y2 complement, the second literal of first clause, think about the second clause, any pairing possible. y2 complement and y1. Can I have a edge like this? No, because variable and its complement, this is not allowed. And y2 complement and y3 complement, this is okay. And y2 complement and y3, that also fine. See. So if you want, you can cross in between. Okay. So I just want to highlight this y2 complement and y3. If you want, you can draw it outside also, but it may complicate things. But you know, okay, fine. And similarly, y2 bar and y1 bar, that also fine, because there is no violation, right? Similarly, then if you look at y2, already y2 to clause 1 it is covered from there to there. So look at clause 3, y2 and y3 I can have an edge, y2 and y1 complement also I can have an edge, fine. And what about y3 complement and y3, can I have this? I can't have this, right? So but y3 complement and y1, this is fine. So like that I drawn the graph. So the graph construction is straightforward. So what you have to do, between the clauses you have to draw the edges, and it should not be from a variable to its negation. Other cases you can consider. So this is how you construct the graph. So this is the first step. That reduction framework is ready. Now let's see how that reduction is done. I mean the how that reduction actually, what is the argument and how we can prove it. So now the our claim is like this. So let me write it as the claim. If f, what is my f? F is actually containing k clauses, okay? Some 3 set problem, okay, or some higher satisfiability problem. If f is, so not if then, because it is a bidirectional proof. Let me write the claim like let me start with f is satisfiable if and only if, because it's a bidirectional theorem. The corresponding graph, this is the formula and this is the graph corresponding to it. If and only if G, I mean the graph, sorry, so this is my claim. If and only if G has a clique of size k. And what about from where this k is coming? Because I have a formula which is C1 and C2 and etc. and ck. So the given for Boolean algebra, I mean satisfiability problem formula is containing k clauses, and correspondingly I have a clique of size k in the new graph. Okay, now this is something you have to prove. Simply saying this maybe by observation it could be true, but I need a rigorous mathematical proof saying that this is correct. Okay, so what we can do, so as it is a bidirectional theorem, you have to prove both direction. So the first direction we will attempt is, so if f is satisfiable, then G has a clique of size k. And definitely the second part will be if G has a clique of size k, then f is satisfiable. So we will prove in both direction. So that will complete the bidirectional proof. Let me prove in this page itself. I thought of taking a new page, but I think this is fine. See, only few steps, the proof is already there. Maybe if you are reading textbook and all, they will be giving a single line proof, but I was trying to explain the meaning also. So what we are supposed to prove is, if the given Boolean algebra in this particular expression is satisfiable, then the corresponding graph contains a clique of size k. Okay, so we can assume that the formula is satisfiable. Okay, so that is the first thing. Assume formula is satisfiable. Assume f is satisfiable. So if a formula is satisfiable, that says that every clause is going to give you a true, because I should get a true from here, I should get a true from here, I should get a true from here, so that and will give me true. So something like that is happening at some point. So that is my assumption. So all clauses are going to evaluate to true, right? Let me remove this. So if f is satisfiable, then all CIs must be true, right? Then all clauses must be true. Now if that is the case, for making each clause true, there will be some literal that is true, right? Because true or something is giving you true, because inside every clause I have this or expression. I know that all clauses are true. Now for making each clause true, there should be at least one literal that is true, because if all literals are false, you know, when you take or between all false, you will get a false. But we already know, as f is satisfiable, every clause should give me a true. Okay, so that within a clause, to get a true, there should be at least one literal. There should be at least one literal that is true. Okay, so and then all CIs must be true. That implies there is at least one XIL. Let me say in the clause I, say the literal L, some random literal, at least one XIL literal which is true. So from every clause I can find such literals which is true, so that the clause is true and all clauses together true means expression is true. Okay, so far is clear, I hope. Now if that is the case, collect all such true literals and make a set. Okay, so I am now making a set of all true literals, in the sense this is a notation, right? In the ith clause I have a literal L like that, such that the corresponding, so this is a notation we used in the graph, and the corresponding literal is something like a x, so something here also I updated the within a clause I have a literal like x y, I1 means clause I first literal, clause I second literal, like that. Okay, so the corresponding literal will be something of the form xil. So that is our notation, and this should be evaluated to true, so that the whole clause is true and all clauses together true means a formula is satisfiable. But we done in the reverse direction, because from the assumption that the formula is satisfiable, we know that every clause should be true for making that conjunction true, right? And now within a clause there should be at least one truth assignment, then only that OR is going to give you a true, like that. So I am collecting all such true cases, so just to pick on only one vertex, okay, which is true. So that will be there. Now can you tell me what about the cardinality of this particular set? What about the cardinality of this particular set? So the cardinality of the set S will be K, right? Because from every clause I am picking on literal. How many clauses are there? There are K clauses in general. We are talking about the general formula with the K clauses. From every clause pick on literal and make this set, so that the set is going to contain K clauses. Now the question is this set S of K, I mean basically this notation IL corresponds to a vertex. Okay, so I have a set of subset of vertices. How many vertices? Some K vertices, because from every clause I am picking on vertex. So is it form a clique? Okay, if it is forming a clique, it is of size K, so that is our claim. So if F is satisfiable, then we have a clique of size K, so that is what we are trying to say. So we are almost done. So only thing that you have to convince yourself that this S is going to form a clique of size K. Why it is so? So just think about it. So this implies S is a clique of size K. So why it is true? Clique in the sense it is a complete subgraph. Every pair of vertices within S should be connected each other. Okay, so take any pair of vertices. Why it is true? S is a clique of size K since for all pair of vertices. So let me take the pair of vertices as one vertex be IL and another vertex be some JM. Okay, so all pair of vertices IL and JM that belongs to this particular S, I mean the set I considered, definitely there exists edge between them. So let me write like that because I don't want to consume more pages, so that this graph everything in a single frame. So that's why I'm trying to prove here itself. Maybe it look congested, but I think you can follow. Okay, so why it is true? Because first thing is you can see that this I and J, definitely they are different, right, between them, since I not equal to J. Is it correct? Because we are selecting on vertex from different clauses. So the first index corresponds to clause. So the clause within a clause I am just selecting only one vertex. Okay, and the second vertex is definitely from a different clause. So these clauses are not going to be same, and also at the same time what is the next thing I need? If I look at the literal corresponds to the first vertex, say xil, and the literal corresponds to the second vertex, say xjm. So they are not complement to each other because we are considering only true literals. Okay, So definitely if one is true, other one is also supposed to be true. So one true, another false, that kind of a situation is not going to happen at all. So this is my requirement of an edge, in the sense this clause should be different and they are not complement to each other. So that is what is happening between every pair of vertices within our S, the subset we are considering, and the size of the subset is k, where k is the number of clauses. So definitely this S is going to make a clique of size k. Hope it is clear. So this is a proof. So line by line, you just if you missed any point, you revise it and try to understand. So still any doubt you have, you can ask me also personally. So hope the proof is clear. The first part is clear. Now we have a similarly one more part. So what I am doing is I just tried to prove it here itself by giving a separator like this. Okay, so let me prove this. So the second part I have to prove is, if G has a clique of size k, then the corresponding formula on the background F with the k clauses that I am not writing is satisfiable. Now how can you prove this? So assume that the graph is going to contain a clique of size k, and you know what is a clique? Every edges are connected each other. Okay, so you consider such a clique of size k, and from that you try to find a satisfying assignment for the formula that says that F is satisfiable. So that is the logic here. So one second. So let the particular clique of size k be, let me denote it like, sorry. So let the clique be something of the form. Say this is a clique I observed which is containing vertices like ij, such that 1 less than or equal to I less than or equal to k, in the sense I am taking, I am having a clique of size k. Okay. So there are k such I part and corresponding literal number be j. So I am just picking some of them. So if you want, you can focus on this particular clique. So what color let me use? Okay, 1 second. Okay, fine. So you know this is a clique of size 3, right, in this graph. So I don't know about the color combination. Let me take this. Is it visible? Sorry, it's not even visible. Okay, let me just take the black color. So this is a, see, this is a clique of size 3, right? Because 3 vertices, 1 1 2 1 3 1, or y1 y2 y3, and I have edges like between every pair I have an edge. So this is a clique. Okay, so as take such a clique of size k. In our example, we have only 3 clauses, so it is enough to look at a clique of size 3. Okay, so something like this. So here also you can see another clique. Okay, now focus on any one of these clique. And what you have to do is, inside this clique there are certain variables which are true, collect them, and there are certain variables which are false, collect them also. Okay, so this is what is the next thing. And for true variables, assign truth value, and false variable assign false value. So that is going to give you the truth assignment. That's all. So what I am doing is, let this set, say S true, denotes set of all what called vertices y, such that this xij is coming from the clique is equal to y. For some y, in the sense, for corresponding to each vertex in the clique, if the truth assignment is true, put it in S true. Now at the same time, if the truth value, I mean that particular literal is complementing literal, say collect them inside S false. So what I am doing is, set of all y such that a particular literal's complement is actually y. Okay, so for example here in here y2 complement I mean, if I'm looking at literal 1, 2, its complement is actually y2. So I'm just collecting that y2. That's all. So the negation literals you collect inside s false, and the positive literals you collect inside s true. Okay, like this for some y. Okay, and now you can see that you can assign a truth value. You just make all these s true. Literals inside s true as true, and all literals inside s false as false, so that this negation will give you true. That is going to be the satisfying assignment for the underlying underlying 3 I mean Boolean formula, okay, which is in the form of 3 set. Yeah, that about it. Just think about it, why it is correct. Okay, let me help you with this example. See, if you are having a click like this, so look at this click. So this is a click, right, of size 3. What is your s true? Just tell me what is your s true. S true is going to contain the true literals like y1, y2, y3. Here all are true. So what will be your s false? S false will be null set, because there is no false variable. So this example is like that. Now let me take this one. If this click is what you considered, you can consider anything as you wish. If you are considering this particular click, you will get s true as null set, because there is no true literal. If something is there, that you have to add here, and s false as is going to contain y2, because that literal complement is y2, something like that, y3 and y1. Okay, so that's all. So now the final truth assignment is something like the true literals you give a true value, like y1 equal to y2 equal to y3 is equal to true. This will be the truth assignment, correct? So if you are making y1 true, y2 true, and y3 true, that makes all the 3 clauses true, and all together that formula is true. So that is a satisfying assignment. Now corresponding to this click, I have a different satisfying assignment, and what is that? If literals are coming from s false, make them false. So y2 is equal to y3 equal to y1 equal to false. This is going to be the satisfying assignment. y2, y3, y1 false means their complements are going to be true, so that all the clauses are true, the formula is also true. Okay, so this is what we are doing. So hope it is clear why it is a valid assignment. So first thing is this, whenever I am considering, I am finding a click, definitely the edges are across the clicks, that is for sure, because click means I need an edge between every pair of vertices within that set, right? Now within a set, if I am saying that these are all the vertices of the click, say y1, y2, y3, I can't, so definitely they are from different clauses. They are not going to be from the same clause. If this y1, y2, y3, any two are from the same clause, that means there is no edge, then I can't call it as a click. Okay, so that is the case there. Hope you are getting it. So if I have a click, definitely the edges are across different clauses. So finally, when I pick vertex, when I focus on each and every vertex from that particular click, I can see that these vertices are vertices belong to different clauses. So now I have a candidate vertex from different clauses, first thing. And if that variable is something a normal variable, I will be giving a truth value as true. If it is a complemented variable, I will give the truth value as false, so that when you take its complement, you will get that particular literal as true. Okay, so that it makes all the clauses true, and the conjunctive normal form to be true, satisfiable. So this is the part. Anyway, I am removing this portion. So for example point of view, I taken this. So when I consider this particular click part, you know how to take that s true and s false. That is what I am trying to say. So let me remove this from here, because see, it's make this already that page is too much complex. Fine. So if you want, let me just draw this subgraph here. So this first case you take, say or the second part you take, say y2 complement. So this is a click, right? y3 complement and y1 complement, and these are also connected. So this is a subgraph of this given graph. I am assuming that it is a click. So so not assumption, I am just taking such a click, and with from that click I am trying to formulate a truth assignment. So what I can do is this, and so corresponding to this s true is going to be the null set, because there is no literal which is true, and s false, if I am looking at it, will be like y2 is there, y3 is there, and y1 is also there. Okay, so hope it is clear. And accordingly I can form the truth assignment as for every true those literals which are from S2 give a truth value as true, and those from S false give a truth value as false. So that is a rule. So this says that y2 equal to y3 equal to y1 equal to false is a satisfying assignment for the given Boolean formula. So that is true, right? Similarly, y2, y1, y2, y3 is equal to true is also correct. That you will get from the top click. Now this is from the bottom click. So hope it is clear. So this is a very important proof, as well as you should know how this something like that is to be proved. Okay. So let me conclude. So what we shown is with this example. So something in general, if I am given a problem, how you can show that it is NB complete, and for that this example you can take. So this is one of the example, and similarly you try to see how other problems are also NB complete and like that. So let me just write it, the conclusion, how to show that a problem, the problem can be any problem, any difficult, any problem, say normally from NB set, problem A is NB complete. So let me tell you, the first step is, the first step is show that A is NB, and it is mostly straightforward, and that you know, right, why it is there will be a non-deterministic polynomial solution unless the problem is not inherently exponential. If that is the case, it may not be the case. It may be non-deterministic exponential times, something like that. Okay, but we are interested on non-deterministic polynomial algorithm, where we have a polynomial time verification part. That is very important. Verification should happen in polynomial times. So that is important. Second point, choose any non-NB complete problem. So, or you can take NB hard also. So typically we take NB complete because it's a very rich set. Say B. So this is another problem I taken. Now third step, what you have to do is give a polynomial time reduction from B to A. So B is something that we already know as an NB complete problem, in the sense from all other problem there is a reduction to B. Okay, now from B I am reducing to A. Okay, so this says that from all NB problem I have a reduction, and it is a well known NB complete problem. So such a problem is what I have taken. So something like this is already there. I don't have to worry about it, and I am just doing this reduction. So this is important. Or I can say that B is reducible to A polynomially, and A is a tougher problem, something like that. So this is what you have to show in the third step. And once you get the reduction, something like what we done in the previous click problem, we drawn a graph. That graph construction is actually the reduction. Okay, that the process is not over yet. You have to show mathematically rigorously your reduction is correct. Okay, show that the reduction is correct, or the argument you are making out of the reduction is correct. In the sense, here your argument is very important, and this claim is important. What is your claim? F is satisfiable if and only if the graph which you shown or reduced is having a click of size k. So that you have to show mathematically. So definitely there are two sides, like if you assume that the formula is satisfiable and show that you are getting a click of size k, and the other side assume that there is a click of size k, then show that it corresponds to a satisfying assignment. And how we can do in both direction, that we shown, that we try to understand very clearly. In the first case, we assumed that let me repeat once again, the formula is satisfiable, and accordingly, means satisfiable formula means every clauses are going to give you a truth assignment, and from each clause there should be at least one literal which is true, then only it will be evaluated to true, right? So we call those vertex, say one from each clause, definitely it will be there provided the formula is satisfiable, and put it in a set, and this set is going to have a cardinality k, because there are k clauses. From every clause I am picking one vertex. Okay, and I can see that or observe that this set S is going to be a click, because if you take any pair of vertices, say IL and JM from this S, there will be an edge, because this rule for edge is satisfied. Okay, they are from different clauses. Accordingly only I chosen the vertex, and they are not negation to each other, because only true values I taken. Okay, fine. So this is the first part, and now the second part is, we already know that there is, assume that there is a click of size. So you can take this click upper side or lower side, two things I shown you, and corresponding to that click, pick all the true literals inside S true and false literals inside S false, and give all true literals the truth value true and false truth value false, and that is going to be the truth assignment. We taken an example, and we saw how it is working, because as it is a click, the vertices should come from different clauses. So that says that I have a click of size M, there will be vertex from every clause, and those clause correctly I am assigning the truth value, so that the formula is satisfiable. Okay, so this is a very important concept, and once you understand this, you can easily follow the reduction to other problems also. So this is something from two different domain, and how this proof sees, if you are looking at the textbook, this set of lines is actually giving you the proof. You can just go through it, and you can now relate this line with what I explained, because I taken an example and I relate everything, every sub steps I explained, but this is something you can see from the textbook. Okay, so that about it. Okay, thank you.